In today's session, we're going to be looking at how we can make use of differentiation when we're working with functions of time. So we've seen already, and this is how it was introduced, that velocity is the rate of change of displacement. We also saw that acceleration was the rate of change of velocity. That phrase rate of change should be familiar to you. That's another way to describe the gradient. And in pure maths, you've seen that you can use differentiation to find the gradient when we have a constantly changing gradient. So when we first looked at velocity, we introduced that as the rate of change of displacement. So here we have velocity as the rate of change of displacement, ds dt. And similarly, we have acceleration as dv dt. So if we have velocity and we're looking for acceleration, we can differentiate. If we have displacement and we're looking for velocity, we can differentiate. This little diagram helps you to remember what to do in what direction. If we're differentiating to go one way, intuitively you should recognize we're integrating to go the other way. So here we're told that a particle P is moving on the x-axis. At time t seconds, the displacement x meters from the origin is given by this function. So since x represents the displacement, I'm actually going to try and swap that out for an s. I'm going to be moving between one motion variable and another, one of our suvat variables. So I'm going to make use of them. So s equals t to the power of 4 minus 32t plus 14. We're first asked to find the velocity of p when t equals 3. So the first thing is actually to find the velocity function. Well, velocity is the rate of change of your displacement. So we can differentiate our displacement function. That gives us 4t cubed minus 32. This is what we're going to use for questions around velocity. So when t equals 3, let's do our substitution. When t equals 3, we get a velocity of 76. And that'll be 76 meters per second. In part B, we're asked to find the value of t for which p is instantaneously at rest. So here's that phrase again, instantaneously at rest. That's when the velocity equals 0 for a split second. Okay, so we're going to set the function equal to 0. The velocity function will set equal to 0. So this is a nice one to rearrange. We're going to add 32, divide by 4, and then cubed root. The cubed root of 8, we all know in our heads, that gets us 2. The final part of this question asks for the acceleration when t equals 1.5. Okay, so acceleration is the rate of change of velocity. We're going to differentiate the velocity function, 12t squared. When t equals 1.5, what does this acceleration function give us? The acceleration is 12 times 1.5 squared. That gives us 27. The acceleration, 27 meters per second squared.